All right, so let's do this example from the video, which I think was trying to find 7 to the 32nd. No, 7 to the 35th. So 7 to the 35th mod 13?
Yes.
Okay. So so here's the setup. Take your exponent and write it as a sum of powers of 2. All right, so throw it into binary, figure out where the ones are. 32 plus 2 plus 1. And then use some law of exponents which says 7 to the 35 is 7 to the sum of these things, which is also a product, 7 to the 32 times 7 squared times 7 to the first. So if we want to find what 7 to the 35th is mod 13, we can simply find what this product is mod 13. And because of the way arithmetic works with modulos, we could find what 7 to the 32 is mod 13, what 7 squared is mod 13, what 7 to the first is mod 13, and then multiply those smaller numbers together. And we should get the same answer. So we reduce any question of this form to basically finding what different powers of 7 are mod 13. And we only need powers that are themselves powers of 2. And that lets us do a trick. So 7 to the first, that's just 7. Okay, and this is all mod 13. 7 squared is 7 to the first squared. So we can take what 7's congruent to, well, it's just 7. 7 squared is 49. And we have to reduce 49 mod 13. Well, 13, 26, 39, and then there's 10 left over. So this is congruent to 10. That doesn't feel right already. I guess it does. All right, so 7 to the fourth is just the square of 7 squared. And we've just found out that 7 squared is congruent to 10. So 7 squared squared is congruent to 10 squared, right, where we got this 10 from here. And 10 squared is 100. And so that's what I started to do here, where 7 squared is 100. So how many times does 13 go into 100? And let me show you how you can do this on a calculator. So do 100 divided by 13, it goes in roughly 7 times. Do 100 minus 7 times 13, you got 9 left over. So that's what 100 is congruent to. Or if your calculator does mods, you can just do a mod. But Desert Island, no mod calculator, but you can add and subtract, right, and multiply. Divide by your moduli, 13. Goes in 7 times, subtract 7 times 13. That gives you the remainder. So this is congruent to 9. So 7 to the 8th is just 7 to the 4th squared. And since 7 to the 4th is 9, this is just 9 squared, which is 81. And we can do the same thing, but 13 times 6 is 78. And so you get 3 left over, so this is congruent to 3. All right, now we got a pattern. Now I don't have to really do any work. 7 to the 16th is going to be 7 to the 8th squared. And 7 to the 8th is 3, so this is just 3 squared, which is 9. And 7 to the 32nd will be 7 to the 16th squared, which will be 9 squared, which we already did up here, which is 3. And now I can write out as many powers of 7 as I want because it's going to alternate 9, 3, 9, 3, 9, 3, 9, 3. But we only have to go up to 32, right? So we take this and we plug it into here, and we can say 7 to the 35th is congruent to 7 to the 32nd is 3, 7 squared is 10, 7 to the 1st is 7. So that's 3 times 10 is 30, times 7 is 210. But I don't want to deal with numbers as big as 210, so I'm going to multiply these two together and say this is congruent to 30 times 7. And I'm going to reduce 30 modulo 13. So 1326 goes in twice, has 4 left over. 30 is congruent to 4. So 30 times 7 is congruent to 4 times 7, which is 28. And 13 goes into 28 twice is 26 with 2 left over. That's congruent to 2. There's your final answer. Does that make more sense?
Yes.
Okay. All right, other questions? So I posted some videos. So video 20 is on modular exponentiation, which we already talked about, but I thought it would be a good refresher, except for the typo. And then 21 talked about prime numbers, and some of that we started to talk about, but some of it we maybe did not get through on Wednesday. So what were the main takeaways from the lecture on primes? What were some of the central ideas? Or weren't there any? Yeah.
Any composite number can be written as a multiple unique prime.
Okay. So any composite number can be written as a product of prime numbers. And if we allow trivial products, we can actually write prime numbers as a product of primes. We could say 11 equals 11, or 11 raised to the first. So really any positive integer bigger than 1 can be written as a product of primes. And I don't know if you said it, but what's the extra detail here?
Each is unique.
It's unique. Okay, if we can write something as, some number n as, say, 3 squared times 5 to the 5th times 11 to the 3rd times 37 squared, we're guaranteed that whatever this number is, there's no other way to write it as a product of primes. It's not also equal to, 5 to the 7th times 13 squared times 23 to the 3rd, right? This is an absolutely unique representation other than the obvious, rearranging the order in which we write these. And that's called the fundamental theorem of arithmetic. So fundamental theorem should be like the most important theorem, right? There's a fundamental theorem of calculus, there's a fundamental theorem of arithmetic, and it's this unique factorization. And it seems pretty obvious if you think about it, because if we were to write this in a different order, then we might be able to write one of these primes as a product of two things, or the product of two primes as a product of two other primes, and that just seems weird. Nonetheless, this is not true for all number systems. It's true for integers, but there's other number systems we can talk about, kind of like complex numbers, where we throw in this new thing called I, right? And we can do arithmetic with it. We can come up with other number systems where we don't have unique factorization. So how many people here have heard of Fermat's last theorem? Okay. This is a problem. It needs to be mentioned more often. So, you know about Pythagorean theorem, right? So, you have a triangle, and you have x, y, and z, and you know that x squared plus y squared equals z squared. And Pythagoras and his fellow cult members knew about this. And have we talked about Pythagoras and his cult? So he 500 BC, something like that. He basically was a cult leader, right? They had this group. It was a secret society, and they worshipped numbers. And they would get together, and I don't know what they did because it was secret, but they believed that numbers were somehow sacred, and that through numbers you could understand, the whole universe. And the numbers they worked with were integers, whole numbers, because we didn't have all these weird things like complex numbers back then. So they believed that by studying numbers and properties of numbers and understanding characteristics of these numbers, they could gain knowledge about the universe. So if you make a triangle like this, and you have a length that's exactly 3 here and exactly 4 here, it turns out the length of this side is exactly 5. Right? Whole number, whole number, whole number. And that's kind of cool. Right? Now, if you make a triangle whose length is like 1 and 1, this is not an integer anymore. It's 1.414 something. Right? So we talked briefly about the fact that they wanted to find fractions of whole numbers that corresponded to this length. And eventually they found a proof that you can't do this. This is what we call irrational. And there's no fraction that corresponds to that. And that's the person they pushed off the boat because he told people about this. So whole numbers are interesting, right? And these right triangles, where the sides are integers, and the hypotenuse turns out to be an integer, those are kind of interesting. And it turns out there's a whole bunch of x, y, z's for which this works, right? So 5 squared plus 12 squared equals 13 squared. I've got a feeling that's not right. Yeah, that's right. Okay, so that's another one. And 50 squared plus 120 squared would be 130 squared, right? You can scale these things up. But the equation x cubed plus y cubed equals z cubed, where x, y, and z are integers, it's hard to find a solution for that. Except the really, really silly solutions like 0 cubed plus 0 cubed equals 0 cubed. Hey, right? But that's not really all that exciting. Or 1 cubed plus negative 1 cubed equals 0 cubed. Well, yeah, that's an integer solution, but it's not really interesting, right? So trying to find an interesting solution to this puzzled people for hundreds of years. And so Fermat, mathematician, 1600s, I think, was flipping through a book on what are called Diophantine equations like this that the Greeks studied, and found a section that mentioned equations like this and the fact that nobody knew of an integer solution to this. And he wrote notes in the side of the books that he would read, right? Most people do. And in the margin of this text, next to the section talking about this, he wrote something akin to the following. He said, there is no possible solution for this equation in integers. Moreover, I've discovered a marvelous proof that in general, this equation has no solution in integers for any n bigger than 2. In other words, x to the 4th plus y to the 4th equals z to the 4th has no solution. X to the 10th plus y to the 10th equals z to the 10th has no solution. And he wrote a note in the margin saying, I've discovered a marvelous proof of this, which unfortunately this margin is too small to contain. And he passed away a while later. And somebody found this textbook from Fermat and found this note in the margin and said, oh, this was Fermat's last theorem, that you cannot solve this equation x to the n plus y to the n equals z to the n. And we know it's provable because he said he had a proof, so we should figure out what that proof is. And for 400 years, people tried to prove this, and nobody was able to. And it's a really, really simple problem to state, right? one sentence, find integers x, y, z such that x cubed plus y cubed equals z cubed. Really simple to state, really, really hard to solve. And in the process of trying to solve this, a lot of mathematics has been developed. So a mathematician named Kummer, I think 1800s, came up with a proof of this. But he mistakenly assumed that in any number system we had unique factorization. And using that mistaken fact, he came up with a nice proof for Fermat's last theorem. And eventually someone said, oh, you've assumed unique factorization, but that's not true in the system you were working in, and showed them why. And he spent a lot of his career trying to fix up that proof, and he invented something called ideal theory. He created these ideal numbers that were like primes in this number system. And ideal theory is a whole branch of mathematics on its own. So this is typical of math, right? You have these seemingly harmless questions that you lift the cover up and there's just this big world of like ugly things and beautiful things underneath there. And as people try to get into that, all this amazing stuff comes out. Fermat's last theorem was proved in the 90s. I think it was 1992. And it came out of a field called algebraic geometry. And I was actually at Duke studying algebraic geometry at the time, so it was really exciting as rumors of this proof started to float around the community. And the person's name was Andrew Weil, and he gave a talk. And it was like all the top names in the field were in this audience of this talk. I was not there, obviously. You know, board, you can find pictures of this because it's historically significant. Board filled with all these crazy equations that don't mean anything to most of us. And he finished one line, there's gasps from the audience, and he's like, I think I'll stop there. And like the people who were in the audience could see from there how to get to the full proof. And it was just built on top of layers of all this different machinery, algebraic geometry and all kinds of other things. But it was a massive proof, right? And it's pretty much assumed that Fermat did not have a proof of this in his head when he read this, right? But there's so many false proofs of this, and he probably envisioned one of those and would have found the error if he had spelled it out. So that's Fermat's last theorem, which I don't talk about in the videos, but you definitely have to hear about it in a course on in a subject on number theory. And Fermat's last theorem is FLT. That's not the FLT that we talk about later in the video, which is Fermat's little theorem, which is proven. Okay, so we'll work with Fermat's little theorem later on. But that's Fermat's last theorem. And if you watch Star Trek and stuff, it pops up in there periodically. All right, so what else was in that video? Unique factorization. Anything else? Yeah.
If you let p of x equal to the number of times less than or equal to x, as x approaches infinity, p of x approaches the natural log of x.
Yeah. Does that seem weird to anybody?
Yes. Weird.
Right? So if you plot the number of primes up to x, it generally, it's got to increase, right? But it's not a smooth curve. It's bumpy, right? If it was smooth, we could find primes. But, you get to a pair of twin primes, and it goes up 2 points in a row, and then it's flat for a while, and then it goes up. And it's a really weird-looking curve. But as you get x bigger and bigger and bigger, it starts to track log x really well. And that's provable a number of different ways, including through the field of complex analysis. So calculus done with complex numbers instead of reals will lead to a proof of this. There's a lot of proofs of this fact. So yeah, that's kind of weird. And that branches into, I think I mentioned in the video, something called Riemann hypothesis and the Zeta function. Those are $1 million questions, right? Riemann hypothesis, there's a standing $1 million prize if you can prove or disprove it. And that's related to this distribution of primes of density. Anything else?
Any number greater than 4 can be prime numbers?
Yeah, so any even number bigger than or equal to 4 can be written as a sum of 2 primes. What is that called?
Gold box.
Goldbach's conjecture. So what's a conjecture? Why isn't it Goldbach's theorem? So what's it?
An idea, it could be disproved.
Could be disproved. A theorem is something that is provably true. Okay. A conjecture is something that we believe might be true, and there's probably evidence to suggest it's true, but it hasn't been proven. This has not been proven. We have, largely through the use of computers, put all kinds of constraints on what a counterexample might look like, and the size of an even number that can't be written like this is ridiculously large. Right? Way bigger than any prime we can actually work with, probably. But it's still not a proof, right? So it's an open question. There's lots of open questions in this area, right? Fermat's last theorem was an open question for 400 years. This is an open question. Twin primes are an open question, right? Are there always two primes that are separated by only two, no matter how large you look? We don't know a proof for that, but it seems to be the case. But it's open. All right. Well, so let's work on some of this stuff. So I posted an exercise set for modular exponentiation. So let's work on this. So we'll just do this at our seats, and then I'll let you go to the board for the next part. So what is 5 times 7? All right, awesome. So what is 35 modulo 3? How do we know that? 3 goes into 35 11 times. That gets you to 33. You got 2 left over. That's what it's congruent to. Alternatively, 35 minus 2 is divisible by 3. So this is another fact. If A is congruent to B modulo M, then A minus B is divisible by M. Why? Because A and B have the same remainder when you divide by M. So if you subtract B from A, you get something with a remainder of 0. Sure. Thanks. So A is congruent to B mod M means A minus B is divisible by M. All right, so 5 times 7 is 35, which is congruent to 2 modulo 3. So find what 5 is congruent to, what 7 is congruent to, and multiply those. So what is 5 congruent to mod 3? 2. And what is 7 congruent to mod 3? 1. And so 5 times 7 should be congruent to 2 times 1, which is just 2. And because modular things do this, right, we expect those to be the same. You can multiply and then reduce, or you can reduce and then multiply. So if we extend that idea, well, so one more practice. So what is 5 plus 7 going to be congruent to? Yeah, it should be congruent to 2 plus 1, which is 3. But we could also take 5 plus 7 is equal to 12. And yeah, and what's 3 congruent to mod 3? 0. Right? And 12 is also congruent to 0 because it's divisible by 3. And so there again, you can add and then reduce, or you can reduce and then add. You should get to the same place. Okay, so using that idea, 7 is congruent to 1. What is 7 squared congruent to? It's just 1 squared, which is 1. And what about 7 cubed? All right, that's 1 cubed, which is 1. And so what about 7 to the some ridiculous number?
1.
Right, it's just 1 to that one ridiculous number. That's still just 1. All right, so that's the warm-up, right? So, so this talks you through what we already did before, but for a different modular exponentiation, 5 to the 1030 modulo 11. So let's go ahead and have you work on those on the board. So let's make sure we get to the right place. I can get that out of your way.
No, I think or I mean, I don't think I 50 is that should.
And then we lost 0.
5 to the 3 is 5 to the 8. 5 to the 4.
So I prefer but not correct.
She hasn't graded.
That's on first. That was perfect. That was 1.
Oh, wait, 111.
Yeah, it's not 11.
Why did it 72?
No, it's just part 1.
Why did I
So we
say
start
it
off
was
just by
1-3?
writing 1030.
That's what we were
which is the
doing.
minus
Yeah,
and
I
that's
know.
the sum.
So it'll be 5.
Yeah. So 5 is 8.
B1.
Oh, yeah, I guess.
Oh, yeah. 5 squared is 25. I don't know.
You're
Or
right.
10 for some reason.
You mean you were thinking 3?
Yeah.
Nice for 81.
Is equal
81.
Oh.
Which is 8,
Someone else did it. 5 to the 8 is congruent to
We're expecting
5 to the 4. I think you can just start skipping to just congruent to 11.
So 81 divided by 11 is 7 times 11 is 7. At least it's all 4
9 squared, remember? So if this is congruent to 9, then this would be congruent to 9 squared.
5.
What were the 4 problems?
Because 5 to the 4 is
I think it's probably
congruent
but they were slow.
5 to the 16.
They're probably
We need the model
You could just
11
Google insert law.
Oh.
So 9 times.
Oh,
So 9
it's
times.
going to be 4. Wait,
But we don't want
Yeah,
to.
it should be. This is congruent to 5 to the 8 squared. Yeah.
9 times.
Got it, just keep going.
Which is 81 times 3 plus.
No,
which is 4 times 3.
This part, we're taking this number and squaring it. The end result after applying the mod 11. So like here we're saying 5 to the 4th is congruent to 9. So we substitute in 9 for 5 to the 4th. So again here we have 5 to the 8th, that's congruent to 4. So in here,
Saying it's 4
yeah,
squared.
that's how congruent it is.
That's it, saying 5 to the 8th squared, which is the same as 4 squared. Which is equal to 16, 11, that would be 5. And then 5 seconds.
We're just putting it
You know, you said 30 seconds, but you wrote 36.
5 and 16, like 16 squared, which is the same as 5 squared, which is the same as 25 minus 11.
Sure.
Like 5, 20, 25 minus 11 is 22.
Yeah, that is.
Yes, 33.
I thought it'd be 4. It would be easy if it was 4.
5 and 64.
Oh.
5 seconds. Just 6 again. 3 seconds squared, which is
Right, this one again, like
is
5.
saying that'd be 9. Oh wait, no, it's not. And then
Okay. Let's just break that.
What is the
That
next
it
one?
repeats.
Yeah.
Yeah.
Okay.
Between 0 and 11.
Oh, wait, no, it's not.
So now we can say
Okay.
Whoa, yeah.
9, 4, 5, 3, 9.
You get something between 0 and 10.
Yeah, probably.
Okay. So I'm gonna write over here. Or do you think you can write it out?
Trying to,
So we just want to write out like S to the 128 is congruent to following the pattern. No, I meant 5, but I
5
said
is right.
S.
Yeah, you just said S.
That's not 5.
That's just how I do my 5s.
Still it's like a 4.
So now we want to revisit this equation and substitute in the congruencies.
So it's 9.
73.
Oh wait.
79. 91. 101.
And then we'll want to isolate the 9 times 3.
Which are
Find out the
factors.
So 27.
27.
Positive, that's a.
81.
Times 3.
And then that would be 34.
No, it should be a bit lower. How does it work? Think about it. You have a 9 and a 5. Is it going to be above 50?
No, not everything.
An easy way to think of it is do 9 times 10 and then divide it by 2.
The other way you could have done this, I don't know if you did this or not, but 9 times 9 times 3, you do 9 times
9 times 9 times 3. How do you get 5 and 9 times 1?
This is 27.
Okay. You can do 9 times 9 is 81, you can go ahead and reduce that.
Oh, yeah, that's fine.
That's going to go to 4, and then you should do 4 times 3 as well.
9 times 5.
Well, in policy,
45 mod 11 is
Yeah, you do 9 times 3. Yeah,
1.
27 is 5.
yeah.
Yeah.
Cool. All right, you got it.
So we can say 5 to the 10
Third
third.
number 21.
Congruent to 1.
Our physics exam.
This is looking good. All right, there you go, perfect.
Because keep having issues and how it works.
Make sense?
Yeah.
All right, cool.
A
So,
little bit confusing and weird, but it makes sense.
yeah, definitely weird and confusing, but cool. All right, so go ahead and start on homework 21.
So but it's also
Do you have it printed out? I'll bring it.
No, I don't have it printed out. Not this week.
well, these are that
It is, but you'll get
more problems than yours.
You got like 13 problems.
Well, I'm saying, is it 33?
Yeah, you got that.
Yeah, it's based on how much the material he thinks you need.
91, 101.
Yeah, it's weird.
That's like it's head up for paper. And then our composite number is 33, which is.
Not really, because if you show that you know 100%, then you know 100%.
Well, yeah, but the line really needs to show that you know.
The first is which of the following numbers are prime?
Actually, no, we'll get 100%.
And then I write them out, so read them off to me.
23,
You could argue that they
73,
show that they know.
79, 91, 101.
Well, that is not how we that your points don't come from your answer, they come from your
C.
So he's essentially just grading.
Well, the answer gets you like points that you're more than a certain number. If you see those stupid algebra error, he's not going to dodge the entire problem because he was very messed up your
I
algebra.
think that 101.
Yeah, not algebra classes, physics, but.
Not sure
So
about 101.
I kind of, I get where it's coming from, but I don't like the
I
Oh, it's
don't
9
like
times 9.
this one.
Because if you see.
Okay, so what's 81 model like? Okay, so this is 81 times 3, that's congruent to 4 times 3.
You could,
Yeah.
you could like not know it, you could show what you know. Put it in 630.
The first program I showed to determine if something is prime.
Yeah, we just set up loops and we iterate through every value for half the lesson. So if it had a factor with the 103, and if they all fail, it's test them.
We literally tried every number.
Yeah, which is really inefficient. Which I don't think you want to try with that many numbers.
Okay, cool. All right, so let me pop up the next one.
Use that as a prompt here.
So we need to do.
Look up prime numbers. Like first 10 prime numbers.
It's pretty much the
And
same.
we could sit here for like an hour testing.
That one's not good. I mean, we have it now. I bet the paper much already copying it.
The next one is 1024.
Oh, it's the tension between.
Oh, right, that doesn't fit.
Yeah, just search first 20 prime numbers and then we'll see if it
Wasn't
doesn't
that
bring
the,
any.
what's it called, not the actual, wasn't the tension thing, from the calculation? Or was there?
So how did you decide what's your prime other than Google?
Well,
we
we
just
just tested
Googled
them
it.
all individually, but then that would take a long time with the calculator.
Yeah. Yeah, 91 is a weird one. It sounds prime, but it's really 7 times 13.
Well, no, they just gave.
I don't know why it sounds prime, but it does to me.
Yeah, it does sound fine to me too.
Thanks for shortcutting that part.
Yeah.
It was the second problem when way to the.
Is it 3?
Yeah, 33 goes 79.
Oh, yeah, it's just 80.
Pretty sure on there. Well, 7 plus 9.
Oh, it's up there?
Oh, wait, no, it doesn't. No, it doesn't.
What is that, Jaguar?
That's fair. We got three long over here.
This is the stuff that I was kind of missing.
Is it? Yeah, it is.
Yeah, that's actually prime.
Yeah, that was confusing also. Because I was thinking like, oh, you were getting. Yeah. It's like, oh wait, where did that go?
Did you give me the one that
Those are actually powers of 2 that are going to add up to the exponent.
If I keep getting free stuff,
I like to do-
I'm aware whoever wants
It's
it.
going to be
I'm aware.
It kind of reminds me of when you're like trying to convert a binary.
7 and 9.
So like, kind of like
Mario.
perfectly, you're trying to break it down.
So you've got
Like following numbers.
Which of the following numbers are prime? Which are composite? What is a factor? 23 is prime. 73 is prime. 91
Products
is
are
prime.
prime?
Wait, 91. 91 is prime.
Could you read me the numbers?
So,
Prime numbers can.
1,260.
Wait, 1,200.
1,220.
Now 33 is divisible by 11.
Very safe.
So write the following numbers as and you do the same thing we did from before.
So like for 25, that would just be 5 squared. I wrote them out for you.
What about 5 times 5?
And F is
Yeah, or 5 squared.
Yeah.
So we're gonna use 5 numbers.
1260. And then you have voltage. We're going to do the 1260.
and man.
numbers that you
And it's like prime for some reason, but it's not.
There's got to be a better way to do this other than with all the calculator, which I'm pretty sure is what he wants to do.
I got the factorization.
I thought composite was just like a number that basically wasn't prime.
Times 5 times 2 times 2. Yes, that is exactly what I did.
That's why like, I'm confused, like I feel like I'm back.
42.
You get factor. You get factor something.
That is 21, which is 7.
Yes, that is what I did.
Alright, so question.
Wait, we're not getting the factorization. We're getting the product of MS primes. So we need to say, like, even if we know their factorization, we're really sure about that.
Well, 7 times 3 is 2 is 1,260.
Yeah, but those aren't primes. Oh wait, yeah, they
Yeah,
are.
they are.
They're all prime.
Yeah, they're all prime.
Well, we are just getting the factorization.
Okay.
1,200.
Yeah, 91 is
That'd be 10.
Well, one is
13.
If one number is the product of powers of prime.
You already know that that's 2 to a power, right?
Yeah, I do.
Why are you doing that?
30.
You're not thinking smart. It's like 2 to the 10?
No, 2, that's way too much.
Yeah, that's
way.
That's like 2 to the...
It's 1, 2, 3, 4, 5, 6.
Oh, what is it?
It's 2 to the 10. I got it right.
No, 2 to the 10th just seems like a huge number.
Yeah, that one needs factorization.
It was asking what is a factor. So now we're looking at what are the following numbers and the product of power of primes. 5, product powers, 5, and 12, 6,
41.
It's 5 and 41.
Yeah.
Are you asking for the definition of factor or?
No, I want to know what the factors
No,
are.
no,
If it's
no.
composite, it means you can write it as a product of two
I meant-
things. So write down what those two or more things are. Any two of them will work.
And that's prime, right?
Let us refer to the list.
I think 41 is prime.
It sure is. Actually, let's rewrite it. He said to write it as powers of prime.
5 squared.
I can get that. Squared.
That's like what they did though.
2 squared.
Is that the only way to do it?
I don't know, but that's like I was thinking. That's like how you figure out what the primes are.
Five squared.
That is the only way to get that.
Suppose you wish to see if the number 1,000,001 is prime. If you divide by every integer between 2 and 1,000,000, how many divisions are needed? 1,000,000 minus 2? Okay. That's 3A. Okay, 3B. Can you divide by only odd integers?
Yeah.
Yes.
I mean, I guess you're technically right. The largest.
Without doing any division, can you put an upper bound on the largest possible divisor of 1,000,000?
So that'd be half of a million.
A million divisions down to half a million divisions. Can you do any better than that?
Without doing any division, man. So actually just say half.
So 1,000,000 minus 2 999,998. What's half of 999?
You're looking for the largest possible divisor. So we're just looking for half of that.
Half of a million is 500,000.
Yeah, just instead of doing the division, just write half. How small can you make that upper bound?
Half of whatever your upper bound is. Or half of whatever the number you're trying to find is. But it'd have to be, so it would be 498,000.
I would argue that if you tested like up to 3, and 3 didn't go in, you could say it would be no larger than 1,000,001 divided by 3. And so on. So like 1,000,000 divided by 5. If that doesn't work, then the upper bound is going to be smaller than 1,000,000 divided by 5.
Well, that would be 1,000,000.
Yeah, but then that starts the process of actually doing it.
Yeah, but this step doesn't say without doing any division. This just says how small can you make it.
And we could test all of our, we can just go through and test all of our numbers and just say the upper bound is 0 because we didn't find it. Because if we're going to start dividing by numbers, then that means we're starting our testing.
You can divide by only 5.
So the first part of it is 25 by 3.
Let's just keep going.
Complicated.
Okay, four examples of n.
Yeah.
And then the second one.
Find four examples of n where 2
Is there a
is
smaller
1 is prime.
There's a much smaller
Find 5 examples where it's prime.
Where 1 minus 1, the next prime.
I'm trying to write them down.
And because you only need the prime.
That's how I got to Or
Oh, we're trying to find where it's not.
I'm just pulling it out, but these are wrong.
Oh, 5.
Because if you want to find the smallest,
Yes.
so the roller that's smaller than
There's 2.
Yeah.
2 to the 4th is 16. That's 15. 15 is not is divisible by 3.
I think what it will be is.
Oh, you know what I think I'm saying? Prime number, when n is a prime number, then that is true. So if we set n equals to
1, 2, 3, 4,
That's the highest number you need.
There's no way that's true.
So 1,000.
If that's true, that's part of like the formula for finding prime.
Even bigger.
For example, if I do 2 to the 23, we know 23 is prime, but this is an even
2 to
number.
the 7. 2
We
to
don't
the
have
7.
to
But that doesn't make
Minus 1.
divisible by 6.
Well, 2 to the 7 minus 1 is 1 to the 7.
Because like the number
Well, if this pattern continues, then they need to find prime numbers.
actually 4 is the middle.
Let's try 5. It's 2 to the 5. 2 to the 5 minus 1. So is this keep going, or does this test fail eventually?
Well, we have to find examples where it fails.
be all the other numbers.
Oh, okay,
Okay, so we know enter the 4 network.
I mean, this test would fail eventually because you need to know a prime in order for this test to work. So eventually you run out of knowledge.
And it's also possible it skips from
Actually, yeah, it does skip primes several times.
We're just giving.
Well, we can do anything that's not. So if we put like 4 in here, so you already did 4. So anything that isn't, if you put something that's not prime into prime, into the
One base 10, but not one base.
Find 4 where 3n minus 1 is prime.
Let's prove that there are a number of primes. We'll prove this by cooperating. Suppose there are a finite set of primes in a set. Let B be the product of all primes on a set B. Let T for trouble, and then you have A minus B plus 1. T for trouble. T for trouble.
I would argue rank 7 not prime.
Well, you can open that up.
You need to find 5. And then you go by next
Okay, suppose there is a set.
You should like write it out like
Well, because we
can do that over some time.
Okay, so there's a set E,
Yeah.
which
The set P is a finite set of all primes. Finite set.
Set P. You have to divide by 7 or 13.
There's a set B. Oh wait, no. B is the product of all elements in P.
About 17.
Yeah, we can do that.
The product of all elements in P.
I think it's
So that one was.
So wait, let's set bounds. So like say P is equal to P1, P2, and P3. Let's assume there are 3 prime numbers.
Yeah, that's what we're just talking about is that pattern. Other people.
1023.
Now, T is equal to B plus 1.
We're trying to determine if the number 1 million is 1.
So when it says B, does it mean?
It
means that's
Or any other?
So can T be prime?
I feel like we broke down. I'm not sure how to prove it, but I think it might be.
If we try it.
1, 2, and 3 is 7. So 7 plus 1 is 8.
Well, 7 would be
Don't move.
to add 1.
Just, other people have to look at that.
7 would be B plus 1 already. Because it's 1 times 2 times 3. It's 6 plus 1 is 6 plus 1 is 7. T is prime. And then if we try it,
we know that the
3, 5, and 2.
you can't have a number go into
6,
a number that's larger than half that shrink or bound. That's what I'm saying. You can possibly be a divisor. Know that they are know that
I'm pretty sure that's prime.
Part B.
Okay.
That's worth it saying.
That's the part.
Number
31 is
You
prime.
know that numbers 19,
Yeah, but since it's on, you know it's not.
How'd you get 30?
11 aren't
So 31's prime. How'd you get 30?
What was that?
And if it's
5 times 3 times 2.
No B
15
is
times
not.
2 is 30, 30 plus 4 is
that. You can start
31,
at
31 is
10.
5.
That's going to be the greatest possible.
Basically, divide by just
1, 2, 3, and 5.
Then that's
No,
still the greatest
well,
possible.
first case was 1, 2, and 3. Now I'm doing 2, 3,
know
and
that you don't
5.
have to check.
P1, P2, P3, 2, 3, 5.
That's not how you're supposed to do proofs.
Question C.
T is always prime. Doing the prime.
Oh,
Equal.
T prime.
So if it
Yes.
has to be about.
So P must be.
Yeah, so if you divide it by 2, you can say it's around 300,000. If you don't do that, it's around 500.
Yeah.
So
So
some
if you
people-
have 1, 2,
So that's
3,
easy.
that's
P
P plus 1.
If you only do the odd ones, then it's half that. So you
Would be 6.
We can't use zero, we can't use one.
How is that
We overachieve.
We're gonna talk about that.
Because it can't be finished, because then T would be part of P.
So we can't divide by 1, you can't divide by a million ones, so it should be is there where you have to try it, 9,000.
Oh, including if you're doing, okay, I thought we were saying.
Nine-
Well,
900.
no, that, I mean, that makes, I thought we were
999,999.
thinking.
Got squared.
So we know T can be prime, but we also Q could not be prime. Then it wouldn't be in that case, then it's like a point.
We're asking if it can. So P must be infinite, because P will be added.
So you can definitely do it with a million divisions.
Occasional.
Upper bound is a million.
I mean, he said that.
But you can actually find a lower upper bound than that. So without actually doing
It's
the
not like a
division,
formal
I
proof.
would go into a million
It's more like a guideline to a proof.
I think he wants a formal proof maybe.
Does he?
Unless it's a $1 million question.
And then you get rid of all the even numbers.
Yeah, I don't understand
We
either.
only have to check out 500,000.
Can we do a little bit
Odd
less?
numbers
Can
up
we
to
do a little
500,000.
less?
I don't know where to go from there.
I think we skipped a lot. I'm not sure though.
All right, so let's talk about this for a minute. Most of you are through question 3 and you're working on question 4. Let me talk about question 3 for a minute. And you can stay at the boards if you want, or you can go back to seats, but let me just kill the lights momentarily. So question 3 is looking at bounds on how many divisions we have to do. And we have this number, 1,000,001, and we want to know if it's prime. So the first order is just divide by every number other than 1 in itself, right? So you have to try 2, 3, 4, and so on, all the way up to 1,000,000. And we don't need to try numbers bigger than this because we know it's not divisible by something bigger than that. So we have all of these numbers we have to divide by, and that's approximately 1,000,000. It's actually 999,999, but it's about 1,000,000 divisions. That's a lot of work, right? The next part observes that we only have to divide by odd numbers. Because if we have an even times an integer, we're going to get an even, and this is an odd number. So once we know it's not divisible by 2, we can toss out all the even numbers. So that brings us down to about 500,000 divisions. So that's a little better. Okay, the next part asks, is there an upper bound on the largest possible factor of this number? So could this number be divisible by this number? We don't have to do any work. We know it's not divisible by this. We know it's not divisible by this. We know it's not divisible by this. How do we know this? Say again? It's greater than half the number. Right? And the largest number that can be a factor is half of the number. So we only have to test up to things that are less than or equal to, say, 500,000, and we only have to test odd numbers up to that. So now we're down to about 250,000 possible factors to test. And we get that for free. We can always do that. We can test odd numbers, starting with 3, going up to half of our number. And if our number is around 1,000,000, we have about 250,000 divisions to do. But that's a lot of divisions, okay? We're going to code some of this up in a few weeks for a programming assignment, and if you do this, your code's not going to finish. Okay, it's going to sit there doing division after division. So we'd like to tighten this up a little bit. And here's the trick that some of you discovered. So suppose we have some number A. That's the number we're testing. And suppose F is a factor. And so A divided by F is Q, whatever the quotient is. Okay, if this is an integer and this is an integer, do you agree with the following? A divided by Q will also be equal to F. All right, so 79 is divisible by 7, you get 13. It's divisible by 13, you get 7. Sorry, 91. So if we divide by the smaller of these, if we test to see if it's divisible by the smaller of these, we don't have to test the larger of them, right? So here's the thing to note. If F is less than the square root of a, less than or equal to, then q has got to be bigger than or equal to the square root of a. Right? Why is this? Because f times q is equal to a. If both of these are smaller than the square root of a, you get something smaller than the square root of a squared, which is going to be smaller than a. And if both of these are bigger, you get something bigger than square root of a squared, which is equal to a. So as f gets bigger, when you divide it into a, the quotient gets smaller. And at some point, those are going to pass each other. As soon as those pass each other, we're done. Because if some number up here divided into a would have given us an integer, that integer is smaller than this number, we would have already found it. So we only have to test up to the square root of a. And you probably saw this in 121 or maybe 120, or someone told you only go up to the square root of a. That's the reason why. So what's the square root of a million?
1,000.
That's 1,000. If we only test odd numbers, that's only 500 divisions we have to try. Right? Which is a whole lot better than 500,000 or a million divisions.
Can we cut it down more by only using prime numbers?
You can cut it down more by only using prime numbers. So if you have a way to keep track of prime numbers, we don't have to see if it's divisible by every number because we know it factors into a product of primes. So we only have to check the prime numbers between 2 and roughly 1,000. And there aren't that many of them. So with that kind of insight, right, we can cut this problem down quite a bit. And again, when you do this in a coding exercise, you'll want to make sure you're only testing for factors up to and including the square root. You got to include it though, because 49, for example, is composite, but you only know that when you try to divide by 7. So, and 7 is the square root, so you got to go up to the square root. All right, so let's take a peek at question 4, which was looking at primes or numbers of the form 2 to the n minus 1. And so some of you got to this point. So 2 to the 1 minus 1 is 2 minus 1, which is 1. 1 is not considered prime. Okay, just by definition, primes have to be bigger than or equal to 2. But 2 squared minus 1 is 4 minus 1 is 3. That's prime. 2 cubed minus 1 is 8 minus 1 is 7. That's prime. 2 to the 4th minus 1 is 15. That's composite. And so on. That's prime. 2 to the 6th minus 1 is 63, which is actually 3 squared times 7. And so on. So the pattern that some of you discovered was that if this exponent is prime, it looks like 2 to that exponent minus 1 is prime. And if this exponent is composite, it looks like 2 to that exponent minus 1 is composite. So the second part of that is true. Okay, 2 to a composite minus 1 is always composite. But 2 to a prime minus 1, we don't know if that's prime or not. If it is, that's what we call a Mersin prime. But not every p has the property that 2 to the p minus 1 is prime. And I think 2 to the 11th minus 1 is the first time that fails. That gives you 2047. And what's the factors of that?
That is 23.
23. So 23 times 89, how's that for a weird combination? So Mersin primes are interesting. And they're always in the Guinness Book of World Records. So the largest known Mersin prime is this number, 2 to the 77,232,917 minus 1. And that's the 50th known Mersin prime. And that was discovered through something called GIMP. That's the Great Internet Mersin Prime Hunt. It's a GIMP hunt. And it's a screensaver you can download and run on your laptop. And when your system's not doing anything, instead of just turning the screen off or showing a box moving around, it'll search for prime numbers. And if you find one, your name is recorded for all of eternity as the discoverer of the 51st Mersin prime. So you can find lists of these. And so this is when they were discovered. So first few were discovered in ancient Greece, and then a big jump until the 1400s, anonymous. Person was embarrassed. And right up through the 1900s, we'd only found 10 Mersin primes, right? And it's a pretty big number. It's 2 to the 89th, which is going to have about 30 digits to it, right? No calculators at the time. So, but these early numbers were found by trial division, right? Keep dividing by possible factors and see if it's prime. Enhanced trial division, I don't know exactly what that is. Now we started using something called Lukas sequences, and this is using things like modular exponentiation and this thing called the Lucas-Lemur test that I mentioned briefly last week. Ways that we don't have to divide by every possible factor. It reduces the set of possible factors. And these are used in GIMP, so Lucas-Lemur test, LLT, and 50s, 60s, this thing just kind of took off. And they start showing which computers were used, right? So old IBM, Big Metal, ILIAC, 360, which was like the most famous mainframe computer, Control Data Corporation, Cyber Computers, Cray Corporation, which makes these awesome machines that have like benches attached to them and they have Freon inside, so they glow blue, beautiful machines. And then somewhere around here, GIMP starts showing up, right? So mid-90s. And most of the primes now that we've discovered, most of the Mersin primes are done through GIMP. So this was just someone's Core i5 running at 3.3 gigahertz, and they found their prime number. So that's fun. All right, so some of these are prime, some of these are not. We have 10 minutes left. Go ahead and start working on question 5. Question 5, we want to prove that there's an infinite number of primes, and this is an outline of the proof. And take 10 minutes and see how far you can get through this in your groups. And it's fairly straightforward once you know what the steps are. But go ahead, and this is mostly just kind of thinking about it in your groups. There's not a whole lot to write, but spend 10 minutes playing around with that.